Okay, empirical formulas. Empirical means from experiment. We can get an empirical formula, the lowest ratio of elements, from elemental analysis by taking a look at the masses of elements that are in a compound. We can look at this by decomposing a compound into its elements or by monitoring the amounts of elements that react to form the compound. We can also find a chemical formula from the percent composition if that is given. It's important to note that the empirical formula gives the ratio of atoms or moles of atoms. It does not give ratio of masses. So these are the steps to finding an empirical formula. First, we need the masses of each element present in the sample. So this may be given from an experiment, the actual masses, or from a percent composition. You take the percent, you can turn it into a gram by assuming a sample size of 100 grams. So if it's 50% carbon, if you had 100 grams of the whole sample, you'd have 50 grams of carbon. So you just take the percent sign and write gram instead. Then we need to convert those masses to moles because that's a ratio that we can work with to find the formula. So that's just using the molar mass. The book says write a pseudo formula using the number of moles of each element as subscripts. You can do that. I think it's an extra step, and so I don't do that, but it's not going to hurt anything. Then we're going to take all those subscripts or amounts of moles and divide by the smallest one. We're trying to get whole number ratios. So if we divide everything by the smallest, that will get rid of any fractions that we have of numbers less than 1. And then sometimes that'll just give us whole numbers. So this is my personal guideline. If the result of that division is within 0.2 of a whole number, you can round it to a whole number. So if it was like 1.15, that's 0.15 from the whole number 1. You could round that. If it was 1.21, you can't round it. Okay? So that's my guideline. What if you don't have whole numbers? There's a couple of approaches. But regardless, we're going to multiply all of those ratios or subscripts by small whole numbers until we get whole numbers. So some of you may recognize decimal equivalents of fractions. 0.5 is the same as 1/2, right? So if you have 1/2 and you multiply by 2, you're going to get a whole number. 0.25 is 1/4, so if you multiply by 4, you'll get a whole number. So you could refer to this table, you could recognize decimal equivalents of fractions, or the trial and error method actually works pretty well here as well. If you don't have whole numbers, multiply by 2, see what you get. If that doesn't work, multiply by 3, then by 4. Usually you don't have to go any further than that. So let's do an example. A sample of a compound is decomposed in the lab and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula. So first step is masses of elements. These are given to us, so let's write them down. 165 grams of carbon and 27.8 grams of hydrogen and 220.2 grams of oxygen. We need to convert these to moles, so we're going to use the molar masses just from the periodic table. So 1 mole of carbon weighs 12.01 grams, and then those grams cancel out. So 165 divided by 12.01. Now technically this would have 3 significant figures. And that would be moles of carbon. The significant figures are eventually going to work themselves out. We're going to get into whole numbers, and so there's no sig figs at the end. The important thing here is keep enough. Keep more than you think you need. Sometimes students will take that and they'll round it off to 14. Don't do that. You're throwing away information and you're going to come up with the wrong answer. So the minimum would be the correct number of sig figs, but I'd say keep 2 extras. So to convert hydrogen, We want moles, so moles go on top, grams go on the bottom. We find the mass on the periodic table, 1.008. And again, always use at least 4 sig figs in your molar masses. Okay. So this one also should have 3 significant figures. I'm going to keep 2 extras. And then for oxygen, moles of oxygen, gram of oxygen. Oxygen here and hydrogen, they are in a compound, so we don't think about them being diatomic elements. That's only when you have the element all by itself, and that's not the case here. So it's just O, and it's 16.00. So 13, this would have 4 sig figs, 7, 6, 2, 5 moles of oxygen. Now you could write a pseudo formula, C 13.738, H 27.579, O 13.7625. And then you're going to do the same thing we're going to do here, but this is less writing. So what I want to do is I want to find out which of these is the smallest number. I screwed this up yesterday. Now I know the answer. It's this one. We all have those moments. We're going to divide everything by the smallest number. So when you're dividing the smallest by itself, that's going to come out to exactly 1. I'm going to divide the moles of hydrogen. This has 3 sig figs. And then for the oxygen, we can see that that's going to be really close to 1, but do the math, because sometimes it can kind of fool you. So this one has 4 sig figs. Again, if you don't want to count sig figs, just keep a bunch of extras. Okay. So this is what we got. We always end up with exactly 1 for one of them. Here, is this within 0.2 of a whole number? Sure it is. It's only 0.007 from a whole number. So we can round that. We can call that 2. This one is also within 0.2 of a whole number, and so we can round that to 1. Those are the subscripts that go, there's my train. C1 that we don't write, H2, O. Any questions? The individual pieces of this are not hard. It's just remembering what was I supposed to do next. Let's do another one. Here we're given a percent composition for ibuprofen and asked for the empirical formula. So the percent composition, what we're going to do is we're going to take the percent sign and just change it to gram. We can do that because if the sample was 100 grams, that's how many grams of each element there would be. The formula doesn't change if you have 100 grams or 1,000 grams, right? So we can just choose whatever's convenient. So I'm going to write down 75.69 grams of carbon, 8.80 grams of hydrogen, and 15.51 grams of oxygen. So same process, convert to moles. Okay, these are the same 3 elements, and so all of that is exactly the same as the previous one. So So 75.69 divided by 12.01. 6.300. No. 30224 moles of carbon. 8.80 divided by 1.008. 87.301 moles of hydrogen. And 15.51 divided by 16. You see what I did there? You see where I screwed up? Anybody? Is 8.8 divided by 1 87? No. I'm looking at my calculator. I lost the decimal point. So I'm going to fix that. It's supposed to be 8.7, not 87. Okay, so I am going to look at those numbers, find the smallest, divide everything by the smallest, because I'm trying to get whole number ratios. So this is the smallest. So that one's going to end up being 1. And this one, so I have to do some division on those first two. 6.30224 divided by 0.969375. 6.50134. 8.7301 divided by that same thing. 9.0059. Question. Now I could round the 9. Can I round 6.5? Nope. That's 0.5 away from the nearest whole number. Not close enough. So I need to multiply. So let's try 2. Let's take that number and multiply by 2. $13.0026. Okay, that's close enough. I can round, right? So that tells me that my multiplication has been successful. So I'm going to call that 13. Now, to keep the ratio the same, I have to multiply everything by 2, right? So I'm going to multiply this one by 2, and I'm going to multiply this one by 2. So this one comes out to 18.0118. Close enough to round, so that one's 18. So it's going to be C13, H18, O2. We're trying to get the lowest whole number ratio. If I multiply this one by 2 and not the others, that changes it. Because I'm starting here with 6.5 to 9 to 1. That's not the same as 13 to 9 to 1. If I multiply 1, I have to multiply all of them in the same way. Any questions? Sometimes when you do these problems, you come out with kind of nice numbers like this, 6.3, that's like a nice number. Sometimes you'll come out with 0.000034557 or something, really tiny. And sometimes students like to freak out about that. No, it just means the sample size was very small. Some of these subscripts can be kind of big, especially if carbon's involved, so don't freak out about that. Now, if you get 50,000, that's probably screwy, but no questions? Yeah?
Why do we multiply by 2 again?
That's a good question. Why do we multiply by 2? I need whole numbers. 6.5 is not a whole number. And I can't just round it. So I have to multiply it by something in order to get it to be a whole number. 0.5 is the equivalent of 1/2. So this is 6.5. If I multiply 6.5 by 2, I get 13, right? And the reason that one of these isn't 1 is that this whole number ratio cannot be simplified, right? 13 to 18 to 2, you can't reduce that at all, okay? Sometimes you have to multiply by 3 or 4 or something else. Any other questions? Okay, so that gives us the empirical formula. What if we want the molecular formula, which we almost always do want because it's a lot more useful? The molecular formula will be some multiple of the empirical formula. It can be the same, in which case the multiplying factor is 1. Or you might have to multiply by 2 or 3 or 4. So in order to find the molecular formula, we need two things. We need the empirical formula, and we need the molar mass of the compound. So in problems that you do on paper, the molar mass is going to have to be given to you, okay? So we want to know how many times do we multiply the empirical formula to get the molecular formula. So the way we can figure that out is we will take the actual molar mass of the compound and we'll divide it by the mass of the empirical formula. And that's going to tell us how many times the empirical formula fits into the molecular formula. So here's an example. The compound has an empirical formula CH and a molar mass of 78.11 grams per mole. What is the molecular formula? So to find N, how many times I need to multiply the subscripts, or what I need to multiply the subscripts by, I'm going to take the molar mass and divide by the mass of the empirical formula. There's just no great short way to write that. The molar mass is given to me, 78.11 grams per mole. The empirical formula mass would be 12.01 plus 1.008. I'm going to be daring and do this one in my head. 13.018. And so 13.018 grams per mole. So we're going to divide those and see what we get. .00015. You should always get very close to a whole number here. There will not be any multiplying here. You should get a whole number. If you're not getting a whole number, then something went wrong. So N is 6. That tells me, now this is not something that you would write. I'm just trying to show you, to illustrate the process here. We're taking the empirical formula and we're going to multiply all the subscripts by 6. So the subscript on carbon is 1 times 6 is 6. And on hydrogen, it's a 1, so that becomes 6. So the molecular formula is C6H6. You see, if I take that ratio 6 to 6 and simplify it, I end up back at the empirical formula, right? You can check this by calculating the molar mass of this formula, 6 times 12 plus 6 times 1, and you're going to get 78. Any questions? So this is what I consider a nice calculate the molecular formula problem, because you were actually given the empirical formula. The hairier ones will make you calculate the empirical formula and then figure out what the molecular formula is. Combustion analysis is a common way of analyzing hydrocarbon compounds. So it's used for compounds containing carbon and hydrogen and possibly oxygen. So what you do is you take the compound and you burn it. And you look at what happens to it. So when you burn a hydrocarbon, all of the carbon reacts with oxygen to form carbon dioxide. All of the hydrogen in the compound reacts with oxygen to form water. And then how do we find the mass of oxygen? Well, we know the mass of compound we started with, and we can figure out the mass of the carbon and the mass of the hydrogen, and so the difference must be the mass of oxygen. So this is an illustration of what a combustion analysis setup might look like. So here we have a furnace in which the sample is burned. We have oxygen coming in there because oxygen is necessary for combustion. The gases that come out of this furnace are run through a series of tubes. The first tube has a substance in it that will absorb water. So this tube is weighed before the combustion analysis, and then it's weighed after, and it will be heavier because it absorbs all of the water produced from the combustion. After it goes through there, it goes through another tube containing a CO2 absorber that will absorb all the CO2. The extra oxygen and anything else will go through and just be gone. Okay? So let's do a problem. Upon combustion, a compound containing only carbon and hydrogen produce 1.60 grams of carbon dioxide and 0.819 grams of water. Find the empirical formula. The first step in finding the empirical formula is finding the masses of the elements. Is this the mass of carbon in the compound? No. It's related to the mass of carbon in the compound. The mass of carbon in this compound came from the original compound, but we can't just use the 1.6. So we need to take the 1.60 grams of carbon dioxide, and we need to figure out how many grams of carbon are in there. So this gets a little more involved. Well, so what I'm going to do is first I'm going to find out how many moles of carbon dioxide I have. I'm going to do that using the molar mass of carbon dioxide. And then I'm going to look at the chemical formula and say, well, how many moles of carbon are in 1 mole of CO2? 1, right? There's 1 mole of carbon and 1 mole of CO2. And then we could convert that to grams, but what's the next step in calculating an empirical formula? You start with the mass, and then you convert the mass into moles. So if I just stop here, I'll have moles of carbon, right? So you can convert it into grams and then convert it back into moles, but why? So 1.6 divided by 44.01. So that would be 0.036355 moles of carbon. And then we have 0.819 grams of water. So I'm going to do the same thing. I'm going to convert that to moles of water using the molar mass of water. And then I'm going to look at the formula. There are 2 moles of hydrogen in every 1 mole of water, right? 2 moles of hydrogen for every 1 mole of H2O. And again, I can stop at moles because that's what I really need for the ratio. The molar mass of water is 18.016. So that's my moles of hydrogen. Any questions so far? This is a variation on the problems we did before. Combining things. Yeah.
Where are we getting the molar mass?
We're getting them, well, I got those molar masses from my head because I use them so often and I remember them. But you'd have to calculate them.
Okay.
Yeah. Carbon plus 2 oxygens, 12.01 plus 2 times 16. Any other questions? Okay, so now we have moles of each element. What do? Divide by the smallest one. Okay, so this is the smallest one. And so, if you want to just say divide by ditto, I'm okay with that. It gets a little tedious. Divided by that other one, the small one. And so this one ends up being 2.50087. But there I have at least the minimum 3 sig figs. What do I do with 2.5? Is that a whole number?
Yes.
Good, decisive answer. No, it's not. It's not a whole number. It's a nice number, but it's not a whole number.
Oh.
It's exactly between, right? So how are we going to make it into a whole number? Multiply by 2. So I'm going to multiply that one by 2 times 2. Now I get my whole number, 5. If I do it to one, I have to do it to the other. That'd be fair. So this one's also times 2, and that gives us 2. So our subscripts are 2 and 5. So C2H5. Any questions? Do not be afraid to make mistakes. I screwed up like 3 times yesterday, and I posted it on YouTube, right? We all do it. That's how we learn. We make mistakes, and we're like, oh, shoot, that wasn't right. Let's fix that. Okay, here's one that's even more fun. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, oxygen produced 1.6004 grams of CO2, 0.6551 grams of H2O. Find the empirical formula. So here we have 3 elements, carbon, hydrogen, and oxygen. We're given mass of CO2, so we can find moles of carbon from that. We're given mass of water, so we can find moles of hydrogen from that, but they don't tell us anything about the oxygen. To find the oxygen, we need to find grams of carbon and grams of hydrogen and subtract those from the original mass of the sample. So this one becomes a little more challenging when you try to show your work, because it can get messy really quick. So I'm going to take 1.6004 grams of CO2. And I'm going to do what I did in the previous example. I'm going to convert this to moles of CO2 and then to moles of carbon. And I'm going to write that answer down because I do need that, but I also need the mass of carbon. So I have 1.6004 divided by 44.01 times 1 divided by 1. So this is 0.036364. I'm not going to keep any extras this time because that's plenty. There were 5 in the beginning. That's moles of carbon. I'm going to need that, but I'm also going to need the mass of carbon. So I'm also going to convert to grams of carbon. And I have run out of space. As frequently happens. Bless you. Okay, so here's our mass of carbon, and here's our moles of carbon. Then we need to figure out the hydrogen. So that comes from the mass of the water, 0.6551 grams of water. I'm going to convert that to moles of water. And then moles of hydrogen. So 2 moles of hydrogen for 1 mole of water. I'm going to write that number down. So I'm going to need that one. And then I'm also going to convert that to grams because I'm going to need that. Grams of hydrogen. Any questions? I still need the mass of oxygen. So this mass here is the mass of carbon plus the mass of hydrogen plus the mass of oxygen. So I'm going to find the mass of oxygen by subtraction. So I've got the total mass, and then I'm going to subtract the mass of carbon, and I'm going to subtract the mass of hydrogen. Now do that on your calculator. Don't try to do that by hand. That's going to be ugly. So 0.8009 minus 0.43674 minus 0.07331. My calculator is giving me 0.29085 grams of oxygen. It's reasonable. That came out less than this, so that's a good sign. So circled, I have the masses of each element. I need the moles of oxygen, so I need to convert this to moles. So 1 mole of oxygen is 16 grams. So I'll divide by 16. And I've got 0.018178 moles of oxygen. It's easy to get lost in this, huh? I have moles of each element now. I'm going to take the smallest one and divide all of them by the smallest. So this is the smallest, right? So when I divide this by itself, I get 1. When I divide this one by 0.018178, I get, let's put this in blue. This gives me 4.0006. And I'm going to take this one up here and also divide by the moles of oxygen. And that gives me 2.0004. So that's one of my numbers. This is another of my numbers. And this is the other one. Can I round those numbers to whole numbers? Yes, I can. Thank goodness, right? So for carbon, it's 2, C2. For hydrogen, the subscript is 4, and for oxygen, it's 1. And so that's the empirical formula. You should be able to do a problem like that for exam 2, just with a periodic table. Any questions?